Hello and welcome to MLOps Minutes. In this episode, we're going to set up the code that will enable us to run our extraction module on Azure ML. Now, there are two things we need to pay close attention to. The first is that we're going to try to couple as little as possible to Azure ML. Why should we do that? Because the idea is that if tomorrow we want to run the whole pipeline on our machine or on another cloud provider, the idea is that we don't have to rewrite the whole project, but that it's very easy to do. The second idea is that all the choices we make here will ensure reproducibility, and that's very important. Here we go. So now we're going to set up our little pipeline that takes our cat and dog data sets with PDFs and extracts images. In the previous episode, we made a little script that automatically creates our Azure ML and automatically creates our dataset on Azure ML. In our case, we based ourselves on data that was in a Git, but in an enterprise, your data may be in a data lake. And typically, you can make a mount point automatically and create this dataset automatically to this mount point, for example. So I've created a second script here, run Azure ML, which likewise takes 4 parameters. So the subscription ID, the group resource name, the name of our Azure ML workspace, and the location, i.e. on which infrastructure, in which country we're going to put our machines. So here we're issuing a poetry run command to a file called AzureML run pipeline PY. And here's what you need to understand. In the train directory, we've set up a real standalone project with a pipeproject.toml generated using poetry. Or we've added the dependencies needed to run the Azure ML version 2 SDK. So that's really all there is to it. It's really a completely independent little project. And now we'll take a look at our file, which executes the pipeline. So in the parameters of this file, we're going to describe it rather roughly. Here we'll receive the 4 parameters we've injected as input to our script. Then there's a step which, if you're already logged in, allows you to log in. Otherwise, it will open the browser to authenticate you, just like the AZ login command, which will open the browser and authenticate you. We'll instantiate an ML client class, which takes the authentication, subscription ID, resource group name, and Azure ML name as parameters. This instance of the class will enable us to control the entire Azure ML API. We'll be able to create, perform operations on the infrastructure, and run experiments. And this is very important. In the following code snippet, we'll create an instance of an ML compute class. Then we'll feed it a begin, create, or update method. Basically, we'll dynamically configure a machine. We'll give it a name and a power. We'll come back to it a little later. Where is it? In our case, it's North Europe. And the maximum and minimum number of instances we want. In our case, 1, but we could use up to 10. If we want to do parallel processing, we could parallelize some processing. And by default, after 60 seconds, with no inactivity, the instance on our machine will shut down, and we won't pay anything if it's no longer in use. So, if I come back here to our portal, here on the left, in the Manage panel, there's a Compute button. And here in Compute, we have 4 tabs, including Compute Cluster. And here we can see the information from my simple CPU load that I've declared. You can click on the new button. The idea is to see everything you can use as a machine configuration. In fact, what makes Azure so attractive is that we're going to have a lot of choice. Now, this is a personal subscription, so I don't have as much choice as an enterprise, but an extremely rich choice of machines with more or less expensive prices. Typically, you can choose machines that cost very little, with very few CPUs, very little RAM, and very few hard disks. On the other hand, you can choose machines that are a little more expensive, but which have certain special features. We can take machines that have, for example, 96 core, 384 gigabytes of RAM, and 768 gigabytes of storage. And what's really nice is that if you need more CPUs, or if you need to do a lot of disk reading, you can choose machines that are fast at reading. And if you need a lot of storage, you can choose machines with really big hard disks. And that's one of the big advantages of Azure ML. The pool of available machines is simply gigantic. And you can really optimize these machines to minimize the cost of an AI train. Here we can also select machines with GPUs so that if the CPU isn't sufficient and we have a training session lasting a month, we can switch to GPUs and drastically shorten the training time. I finished with this little aside, but it's very important. Next, once you've instantiated a pool of machines, you can create a pipeline. In our case, for now, it's extremely simple. We'll create a method here which will take as its parameter a link to our folder containing our PDFs, and we'll feed it to a component here, which we load via a YAML. Why do we do this? Because the idea is that our step extraction is really a separate project. In other words, we're just launching our experiment, but our extraction stage is a completely separate project that will run in isolation. And for the time being, we're running it on our own. As a parameter to this pipeline, we're going to inject our dataset that we've created automatically. So how do we get this link here? What happens is that if I go back to my data, here, last time, we automatically created this dataset. I'm hoping it'll appear soon enough. Here, we'll find the name, the URI to our dataset, just copy it. And paste it here. This will effectively make available this list of PDFs we uploaded in the previous episode to our script. So here, I've got a list of PDFs. The path may be a little long, but I've got a real list of flat PDFs that will be available in a directory. Back to the code. Now we create a job to trigger our experiment, which does a creator update. And we give it a name of experience of experimentation that we called cat-dog-other pipeline. And finally, here we tell it, I'm waiting for the end of the pipeline to hand over to the rest. This file will remain stuck on this line until it's finished. So I know it's very rich, but now we can go back to our little .yaml file here. And we're going to arrive in the extraction module. And now our entry point is this .yaml command. And here we're going to declare in pure declarative mode. There's no code, so we change projects. We're going to configure the characteristics of our little step on Azure ML. We'll give it a name, an extraction, a version. Now we're going to say, is it deterministic? We're going to say yes. In other words, in relation to a given input, if the input is always the same and the code hasn't changed, well, that means the output will always be the same. And this means that Azure ML automatically will cache. If we run the whole experiment again and change neither the code nor the input, well, by default, Azure ML will reuse the output from the previous experiment. And instead of taking 15 minutes, it will be almost instantaneous, and we won't pay anything at all. As input here, we must declare what we receive as input. So in effect, the URI will be to our input folder, and as output, we'll get a URI to a folder containing our flat images. We're going to create what we call an environment. This is a very important choice I've made. By default, Azure ML uses MLflow, which lets you use Conda files. But for us, the problem with Conda is that it uses PP behind it, and it doesn't allow you to take an exact snapshot of all your dependencies at any given time. So with Conda, it's possible to rerun an experiment 2 weeks later that has already taken place, doesn't download the same dependencies, and causes our experiment to stop working. And that's not what we want. We want to be reproducible. So what do? Our project, remember, we used a poetry.lock. And we're going to use a Docker. So we're actually going to build a Docker, run our step on a Docker to be able to run our pipeline rather than in our Docker file, having used Poetry directly. What we've done is to generate a requirements txt file from Poetry, which will take an exact snapshot of all the dependencies at a given time. To generate this requirements.txt file, we created a makefile as the project's input. This makefile, which will of course be run automatically in the CI/CD, will automatically extract the requirements.txt file each time the project is built. So before launching the pipeline, we update the requirements.txt file. So behind our Docker file here, we're going to describe it because it's important. First of all, we're going to specify the exact version of Python we want to use. That is, on my workstation, I couldn't use the latest version of Python 3.10.13 because I can't install 3.10.13 on Windows, but I want the security patch. So I'm going to freeze this version 3.10.13, which I'll use for training and production. Then I'll copy my requirements.txt file and download it. I update pip and download all my dependencies that are in this toyxt file. Then I hand over to AzureML, which will be able to trigger its processing. Here, I've given it an environment, knowing that I can specify a machine for it. Here, by default, it will use the compute I've created, but you could very well create different machines for each stage of AzureML to say that this box will run on a machine with a GPU, another will run on a fast reading machine or with lots of RAM. It's pretty flexible. Here we're going to specify that the code I'm executing is all in this directory, and I'm going to execute a command here, which will trigger a command.py file with my PDF input directory as input and a path to an output directory as output. When I do this, it's not all I've done. In addition to this file, I've also added an .amlignor file so that I don't have to push the Azure ML tests into my little box. And here, locally, I have my cat and dog dataset, and I don't want to push it into Azure ML. So I created an .amlignor file that lets me ignore certain files. The same goes for Docker, where I've created a .dockerignore file, because when you build a Docker, it will take the current context and send it to Docker. And here, as I have 4 gigas of PDF files, I'm not going to send it to the Docker context. It'll take a really long time for it to spit out. Once I've done that, I run my command.py file here. And there you can see that I'm using my little library that we created last time, that we used in the unit tests. And here we haven't modified the code at all. You have to understand that as we worked in TDD on my workstation, I didn't link my code to AzureML at all, and it's completely independent of AzureML. And it's not just Azure ML. You'll see there's a dependency here on ML Flow. ML Flow is a standard for this type of workflow. But ML Flow is still a framework. And we're also going to make our code as ML Flow independent as possible. This is the only coupling we have with ML Flow. So it'll be in this file. We'll retrieve the arguments to our PDF input images and the output folder. We'll instantiate an instance of our class that extracts the images. And we'll run it with our input folder and our output folder. We'll even log metrics with MLflow. We'll tell you how many files are in input and what is the number of output images. Do I have anything else to say? I think that's about it. The idea is that we've just created a launcher which is not coupled to Azure ML. On the other hand, the coupling to Azure ML is done with this YAML file, which is quite light. And as we've used Docker and Poetry, we'll have a completely fixed picture of independence and also of the Docker file, which will enable our stage to be extremely reproducible. And that's really what we want. Now, what I can do is, if I want, I can go back to my launcher, run AzureML.sh. I can reopen Git Bash, do run AzureML.sh from my train directory. And automatically, it'll run my pipeline. And pretty soon, if I'm already authenticated, it'll take over the existing authentication. Otherwise, it'll open a web page to authenticate me. Here, I already had to be authenticated. And pretty soon, the job tab will appear. Here, I have experiments. So here's my cat, dog, and other experiment. And pretty soon, it's going to launch this pipeline. And since I've already run it, it's already been run successfully. What's going to happen is that pretty soon over here, you'll see a little loop appear. That means it's reused the previous experience from the caches because no input or code has evolved. So it's not going to rerun the box. We're going to make money. It's important to know that launching this type of experiment doesn't cost that much because the first time it's going to have operating time. But basically, our cluster will launch. We'll pay for the cluster's time. If it's 15 minutes, we only pay for 15 minutes, and that's it. Here you can see an overview. We can now see the input data set. Here we can see the link to the output folder that was generated. Here in the metrics tab, you can see the number of input and output files. So here, I've had over 8,143 PDFs and 36,999 images output. In terms of logs, it can be interesting because you can see the logs. I haven't included any in the code, but here you'll see the Python prints displayed. And we can also find the logs of the construction of our Docker image. If I now return to my output folder, I can explore it in the Azure portal to see what it looks like. And with a bit of luck, I'll find all the images that have been extracted. So that's great. Normally, I'd have to... Can I just hang on a sec? Maybe I should have done Explore. Maybe that's a bit better. So now in my output set, I can explore what's been generated in the output, and I'll see the images that were extracted from my PDFs. And there you have it. In any case, thank you for this very rich episode, and I'll see you soon for the next stage. Now we're going to trigger all this from a CI GitHub action. Thank you, and see you soon for more videos.